This is William Gibson and Ryan Connie doing a lightning talk on bad apples, orchestrating movement and execution via native macOS protocols. Take it away, guys.
Sounds yes. All right. Hi, everyone. Thanks for having us here. Excited to be here at BSides Buffalo. I'm William Gibson, and this here is my coworker Ryan Connery. We both work for a company called Cisco Talos, and today we're going to be talking about our research that we got published recently called Bad Apples, Weaponizing Native macOS Primitives for Lateral Movement and Execution. So the core idea of this research is simple. As macOS becomes more common in enterprise and developer environments, attackers do not always need custom malware or novel exploits. A lot of interesting capability already exists inside the operating system, go through AppleScript, remote application scripting, Finder, Spotlight, metadata, LaunchD, and built-in transfer utilities. So my portion of the research focuses more on macOS execution behaviors, whereas my coworker Ryan's here focus more is on lateral movement. So today we'll connect those together in one post-access story, and my friend Ryan here is going to start by framing why all this matters now, and especially for Mac enterprise fleets.
So historically, the enterprise has been made up of mostly Windows devices, and up until recently, we've seen a bit of an uptick in that share going more towards macOS devices. Because of the historical context of the market share, we feel that there is less of a focus on macOS security compared to something like Windows security. Some of this uptick that we have seen or have observed has primarily been with roles that are software developers or IT professionals or people in the C-suite, executive level. Because we are seeing an uptick in roles such as these that are using macOS devices, we can expect that these machines are going to have things like source code or SSH keys, cloud credentials, or sensitive business documents on them, which would make them a prime target for attackers. And when we approached this research topic originally, we came in with the assumption that most of the lateral movement would be performed with a more SSH-centric approach. And as such, most of the things that would be monitored would be more SSH artifacts on the device. And this was kind of backed up by some of what we saw on the Lubin's project, which is the macOS version of the WALDAS project. I think there was only maybe 2 binaries that were marked as lateral movement, and they were both leveraging SSH as well. So we wanted to take more of a focus on tools that were Mac native or easily obtained through a package manager such as Brew, and preferably would not have a reliance on SSH.
So technical difficulties. All right. So this slide here is important because we do not want people to walk away thinking that this is one quiet sequence. These are distinct technique families. We looked at remote application scripting and Apple's event speed for remote control. We looked at OSScript and Terminal as execution paths. We looked at Finder for discovery and Spotlight and metadata for staging. We looked at launch agents as a persistence trigger. And we looked at multiple transfer channels such as SCP, SMB, NetCat, and SMB traps, and SOCAT. In real instances, these may appear independently, but an attacker may use only one or two of them. So correlation should come from telemetry, not from assuming every behavior in this stack. So to understand the first set of behaviors, we need to understand what RAS is, or remote application scripting. So remote application scripting, formerly known as remote Apple events, extends AppleScript inter-process communication across a network. Under the hood, this uses the ePPC protocol and Apple Events-D. The important point of this is that remote application scripting is not a malware feature. It is a legitimate administrative and automation feature. A controller can send Apple events to a scriptable application and on the target Mac. The target application then performs some sort of action locally. This changes the way we need to think about remote activity. Instead of a traditional model where a remote login spawns a shell and runs commands, remote application scripting allows one Mac to remotely influence applications on another Mac through application level IPC. That changes the way, for defenders, the pivot identifying cross-host IPC and application level behavior, not just shell commands. So once we have an understanding of remote application scripting as a remote control primitive, the next question was whether we could turn that into a form of execution. This is one of the more interesting parts of our research from my side. A straightforward idea would be to have remotely tell system events to run a shell command, but macOS blocks that path with a familiar negative handler behavior shown in our published research. So in other words, there's an international security boundary that prevents that direct remote shell execution. The useful finding was that Terminal.app behaves differently. Terminal is designed to accept script-driven terminal actions, so instead of treating remote application scripting as this thing that executes code directly, we treat a remote application scripting as a control layer and a terminal as the execution proxy. Conceptually, the flow looks like this. Remote application scripting sends Apple events to Terminal.app. Terminal starts the shell side behavior. The payload material is transported in a safer encoded form, decoded onto the target, permissioned, and then invoked by the shell. The key defense point is that the suspicious behavior is not just base64 exists or bash exists. It is the lineage and context behind it. Apple events the influence of terminal, terminal producing shell activity, and remote automation and context behind it. Up next, we're going to show some related movement case using remote application scripting not just to execute, but to discover useful information on a remote Mac without a normal shell. So from a lateral movement side, remote application scripting is also useful when you are not trying to execute payload. Because Finder is scriptable, a controller can use remote application scripting to ask Finder on the target system for information. For example, from the research we were doing, we queried mounted volumes. When you query mounted volumes, you can reveal network shares, external storage, and other useful context without creating the same kind of interactive shell telemetry defenders may expect to find in the logs. This matters because a lot of detections are focused on process execution trees, but with Apple events, some of the interesting action is happening through application behavior and IPC, or inter-process communications.
Want to try this real quick?
Yeah, sure.
Detected by the monitor by your system. Maybe you want to try that instead.
So I'm going to start off the top of the slide here real quick, but from the lateral movement side, remote application scripting is also useful even when you're not trying to execute. Because Finder scriptable or controller can use remote application to application scripting to ask Finder on the target system for information. One example for research is that we record mounting volumes, which can reveal external network shares, storage, other useful context without creating the same type of telemetry logs that we expect to see. So this matters because a lot of detections are focused on process execution issues, but with Apple events, some of the interesting actions happening through application behavior or inter-process communications. So if the detection strategy is only like show me suspicious shell commands, this type of discovery will be required. So of course SSH still matters. The nuance is that even when SSH is a transport, macOS automation can change what the activity looks like. So SSH is still the obvious common transport. But one of the things we wanted to highlight is that SSH into a Mac does not only mean classic shell commands. When an attacker can invoke OSAScript over SSH, they can interact with AppleScript's capabilities. That can include system information, Finder manipulation, GUI automation, or shell execution through AppleScript handlers. So defenders may see an SSH login and think they understand the session because they have the SSHD and shell logs. But if OSAScript is used, some of the impact may occur through Apple events and GUI or Finder. Finder side effects rather than a single command tree. So the important detection point is to treat OSAScript as a connect normal remote session to macOS automation surfaces. So yeah. So one of the next things we want to talk about is one of the stranger areas of our research where we use Finder comments and Spotlight metadata as a staging space.
Yeah, so as Billy mentioned, remote application scripting typically interfaces with a Mac application. So we wanted to see if we could use this relationship to kick off our lateral tool transfer research. We also kind of came in with the understanding that a lot of endpoint security products will either be fingerprinting or scanning file contents to determine if it's malicious or not. So we wanted to try and think outside the box and see if there was another way we could stage payload. And that's where we became aware of Spotlight metadata. So if we use remote application scripting plus Finder, we can create an arbitrary file, and then rather than write to its file contents, we can write to the Spotlight metadata to store a payload. The payload can later be obtained, decoded if necessary, and then executed. And this is kind of a little more of an interesting way that we found to transfer a payload to a target device. And while the talk is mainly on lateral movement and execution, we couldn't ignore the opportunity of persistence here. So we were thinking that we could have a plist in the user's launch agent directory that would then use Finder to read the comment on the file, decode it if necessary, and then pipe it to some script interpreter for execution. And that takes us to a few more lateral tool transfer methods that we researched. As we kind of mentioned from the beginning, we wanted to look at things that weren't just SSH. At the top of the list, we see secure copy and SFTP, which use SSH under it. That was kind of just our baseline, but we wanted to look at some other things that were not just SSH. We also wanted to look at things that might blend in with that typical enterprise network traffic that we might see, and we mentioned that more software developers and IT professionals have been adopting that. So we wanted to see if things like Netcat and Git could also aid us in tool transfer. And last, we wanted to kind of look at things that, technologies and tools that may not be typically associated with tool transfer, but we could repurpose for movement. And we just wanted to shine a spotlight on a couple of the methods that we used. The first one was SNMP traps. So SNMP is typically used for monitoring network devices. And by using traps and customer IDs, we could successfully transfer a payload from one device to the other. TFTP, which is typically used for bootstrapping devices and firmware workflows. kind of falls under that IT typical workflow traffic that might blend into an enterprise. And finally, SOCAT, another tool that is not as popular as NetCap, but still used by network professionals. Might not typically be viewed as something that could be tool transfer utility, but we thought that might be a convenient blind spot that we could take advantage of. So we kind of wanted to showcase here that rather than just hunting file names, we should be looking for the behaviors of some of the techniques we executed. We want to be looking at things like unusual process lineage, like with the RAS execution, anomalous behavior, such as frequent reads and writes to file comments, and lastly, unusual or abnormal peer-to-peer traffic as it pertains to SNMP, TFTP, and tools like that.
So the controls should map to the behaviors. Do not treat this as one monolithic structure. For remote application scripting exposure, defenders should disable remote application scripting by default and only allow it on restricted devices. The same goes for remote logging, which should be explicitly managed, not casually enabled across the fleet. For transfer services, disable or restrict TFTP and SNMP services. Monitor for launch new changes that enable network-facing games unexpectedly. For network exposure, use the macOS application firewall and stealth mode where appropriate to reduce unsolicited reachability. And for the execution side, TCC is very common, also means transparency, consent control. The automation category governs whether one application can control another. If an unexpected script or process tries to control terminal or finder, that should be restricted through NPM or mobile device management where possible and treated as being a full signal Windows code. The larger point is that macOS already gives defenders some control points. The challenge is making sure that they're deliberately configured and monitored. So we'll close this main section of our research here with the takeaways we want defenders to remember here after this talk. So the main takeaway here from Bad Apples is that macOS movement and execution primitives are native, persistent, and huntable. They are native because they use things like Apple built for administration, automation, metadata, and file transfer. They are persistent because some of these mechanisms like launch agents and metadata backstaging can survive beyond a single command or session. And they are huntable because they create patterns. Apple events, D lineage, EPPC references, finder metadata writes, base64 decode change, launch D triggers, and unusual peer-to-peer transfer protocols. So our recommendation is to model remote application scripting, monitor metadata, and constraint services. If you do these three things, you make the class activity much more visible in your environments. So to close this off here, the question you want everyone to think about is, where do you see these behaviors today? Do you have visibility into remote application scripting and EPPC environments? Do you find your metadata rights? Can you identify peer-to-peer transfer protocols between Macs? And can you distinguish a proven admin automation from unexpected automation? If the answer is no, that is the gap this research is trying to highlight. These are the native macOS privileges, so the solution is not just malware detection. It is behavior modeling, service control, and telemetry coverage. The point of this research is not that every Mac environment is being used this way today. The point is that the primitives are already there. Remote application scripting, Apple events, finder metadata, launch D, and native transfer utilities can all support movement and execution when it is used. The defense opportunity is to model those behaviors, restrict unnecessary services, govern automation through TCC and NDM, monitor metadata operations, and correlate process lineage with internal network activities. These bad apples are native, but they are also huntable. We'll keep these next few slides here brief since we had some technical difficulties and stuff. Yeah, to start us off here, we'll go ahead and get a QA, and then we've got some appendix slides if anyone wants to see those afterwards. Do we have any questions? good. No worries.
And shoot, I'll take a shot. When you were using, it was AppleScript to use Terminal as the proxy and then do all this assorted stuff. Is part of the reason that that's able to work better because Terminal.app has more privileges built into it?
Yeah, it has more accessibility, into which that's where we were then able to encode the AppleScript itself within the base64, to which normally within the normal terminal shell. As we mentioned, if you look into our published research, we'll go more in depth with it, but you get some nasty handling errors and stuff like that. You don't like that, you don't want you to do that. But the moment you encode it and deliver it to the terminal as a proxy and tell the command to decode it, all of a sudden you got some pretty mean scripts getting written onto your computer, which, as we mentioned, within the logs itself, don't come out cleanly. There is there are correlations to be made. There's patterns to be recognized to understand that, oh, this isn't malicious actually to put something in our environment. Like I said, you're not going to just see a shell command be executed and all of a sudden all these different behaviors happening. It is a sequences of certain behaviors that need to be recognized and properly monitored within the environment, especially for buildings where majority of your employees are being working with some background times like this one here. So I appreciate the question. Thank you.
Cool.
So yeah, if there's any more questions, don't mind push past it, but go ahead and we'll show off some of these slides here. If there's interest, this, so right here, got our technique family mapping that's demonstrating the different technique families. Yeah, remote application and scripting remote execution maps, so software deployment style execution, terminal as a proxy. Remote application scripting level discovery maps for remote services, and application control over PPC. Lateral tool transfer maps to Technique T1570. Style moves of tooling, launch agents provide the persistence trigger. Fun information stuff like that.
Thank you very much.
Yeah. Got some more sites here. Before the screenshot. This one. All the hypotheses that we kind of had while we were doing the research and trying to work with ideas on how we can try and break the environment a little bit. And then, yeah, that's it.